Have you ever really stopped to think about light? Really think about the incredible secrets it's hiding. Today, we're going to pull back the curtain on the elegant, simple rules that explain how light bounces off mirrors, how it bends through water, and how it can even be trapped inside a tiny glass fiber to power our entire world. Let's jump right in. So, how is it possible that the same physics explains trapping light for the internet and the illusion of a desert mirage? Well, the answer to both lies in the principles of ray optics. This is the hidden science that connects the reflection you see in the mirror every morning to the giant telescopes that are peering across the cosmos. And you know what? It's not magic. It's just really, really cool science. So here's our game plan. We're going to start with the absolute basics. What is ray optics? Then we'll explore how light bounces, that's reflection, and how it bends, which is called refraction. After that, we'll see how we can trap it completely. And finally, we'll look at the amazing ways we've harnessed all these principles in some of the most important inventions in human history. So let's start at the very beginning. What exactly are we talking about when we say ray optics? At its core, ray optics is all about making things simpler. Look, light is complicated stuff. It's a wave, it's a particle, but for most of the things we see every day, we can just pretend it travels in a perfectly straight line. We call that line a ray. And this simple model works incredibly well, just as long as the things light is hitting are way, way bigger than its own tiny wavelength. And that's really the whole idea. A ray is just a line, an arrow, showing which way the light is going. It's the basic building block for literally everything else we're going to talk about. Pretty simple, right? Okay, so this brings us to a really key distinction. You can basically split everything in the universe into two camps: things that make light and things that just borrow it. The sun, a lamp, they're luminous. They create their own light. But the moon is non-luminous. The only reason we see it shining up there is because it's acting like a giant mirror in space, bouncing sunlight back down to us. And guess what? The same is true for just about every single object you can see around you right now. All right, let's dive into our first big topic. Let's see how this all builds, starting with what happens when light hits a surface and bounces right off. This, my friends, is reflection. Just think of it like a tennis ball bouncing off a wall. When light rays hit a surface, whether it's a perfectly smooth mirror or the top of a lake, some of that light gets sent bouncing back. That bounce is reflection, and it's the whole reason we can even see those non-luminous objects we just talked about. But here's the thing. This bounce isn't random at all. It's perfectly predictable, and it follows two super simple laws. First, the angle the light comes in at, the angle of incidence, is always exactly equal to the angle it bounces out at, the angle of reflection. They're a perfect match. And second, the incoming ray, the outgoing ray, and that imaginary 90-degree line called the normal, they all stay on the same flat plane. It's neat, clean, and always follows the rules. Now, this is where things get really interesting, because once we know the rules, we can start bending them, or, well, bending the mirrors. A concave mirror, which curves inward like a cave, takes parallel light rays and focuses them all down to a single point. It's a converging mirror. But a convex mirror, which bulges out, does the exact opposite. It scatters the light, making the rays spread apart or diverge. And believe it or not, there's a beautifully simple formula that lets us predict exactly what these curved mirrors will do. The mirror formula connects the object's distance from the mirror, that's u, with the image's distance, v, and a special property of the mirror itself, its focal length, f. With this one little equation, we can design everything from the mirror you use in the morning to the massive telescopes that explore the galaxy. Okay, so we've got bouncing down. But what happens when light doesn't bounce? What if it goes from one thing into another, like from the air into a glass of water? Well, it bends, and this phenomenon is called refraction. So why on earth does it bend? It's all about speed. Light actually changes speed as it moves through different materials. Imagine a light ray zipping through the air and then hitting dense water. It's forced to slow down, and that change in speed makes it pivot, changing its direction. The color of the light, its frequency, stays the same, but its path gets a little kink in it. And this bending creates some really classic optical illusions. You've probably experienced this yourself. If you've ever tried to grab a coin from the bottom of a pool, you know it's never quite where it looks like it is. That's because the light from the coin travels from the water, bends as it hits the air, and then reaches your eye. Your brain, which is wired to think light always travels straight, gets tricked into seeing the coin in a shallower spot. We call this apparent depth. Now, what if we could combine what we know about bouncing and bending? Well, you get something that seems totally impossible. You can actually trap light. This amazing trick is called total internal reflection. This mind-bending effect only works if you have two very specific ingredients. First, the light has to be trying to go from a dense material into a less dense one. So think from water out into air. And second, it has to hit that boundary at a really shallow angle, an angle that's greater than what we call the critical angle. And when you get both of those conditions just right, something incredible happens. The light doesn't bend. It doesn't escape at all. It reflects perfectly back into the water, basically becoming a prisoner of its medium. This is the secret sauce behind the fiber optic cables that carry the internet. A pulse of light gets shot into a super dense glass core. It hits the edge of the less dense outer layer at a shallow angle and bam, total internal reflection. It just keeps bouncing perfectly down the line for miles and miles, carrying all our data with it. And get this, the exact same principle explains mirages in the desert. On a scorching hot day, the air right above the road is way hotter and less dense than the air above it. Light coming down from a distant tree bends as it passes through these layers. Eventually, it hits a layer of hot air at such a shallow angle that it totally internally reflects upwards, right into your eye. Your brain traces that light back in a straight line and sees a reflection on the ground, making you think there's a puddle of water there. Wild, right? Okay, so we know how light bounces, and we know how it bends. The last piece of the puzzle is to see how we've learned to control these effects on purpose, using what we call optical instruments. And the hero of most optical instruments is the lens. Now, while mirrors use reflection to control light, lenses use refraction. By carefully shaping a piece of glass, we can bend light rays in very specific ways, either to bring them all together to a single focus point or to spread them apart. This gives us the incredible power to magnify our world. And this power led to two of the most revolutionary inventions ever: the microscope, which uses a combination of lenses to make tiny, nearby objects look huge, and the telescope, which uses a similar set of principles, not to see small things, but to gather up faint light from massive objects that are unimaginably far away. But here's a really clever engineering twist. It turns out really big lenses have a problem. They tend to bend different colors of light slightly differently. This creates a fuzzy, color-fringed image called chromatic aberration. The brilliant solution? Just get rid of the main lens entirely and go back to reflection. Today's biggest invest telescopes use enormous concave mirrors to collect starlight. Mirrors don't have this color blurring problem, and we can build them to absolutely gigantic sizes. So let's do a quick wrap-up of what we've covered. Ray optics is our simple model where light travels in straight lines. Reflection is light bouncing off a surface according to simple rules. Refraction is light bending as it changes speed. Total internal reflection is the perfect bounce that lets us trap light. And by mastering all of this, we can build incredible tools, like microscopes and telescopes, to explore literally everything. It's pretty amazing when you think about it. From understanding one simple ray of light, we've built the technologies that define our entire modern world. We've mastered the visible to see across the universe and deep into the building blocks of life. It really makes you wonder, what invisible frontiers will we illuminate next? Thanks for diving into this with me.